Hi all, welcome to this video. We're going to be going over a quick SVD of the matrix A that we've shown that I wrote down. And I also wrote down A transpose A and AAT, which we will use. And we're trying to decompose this to U, U sigma V transpose. And if you guys have a textbook, you'll know what those mean. But for now, we're just going to be going over the steps. Okay, so the steps we're going to do is first find the eigenvalues of either A, ATA, or AAT. And once we find those eigenvalues, then we will determine the eigenvectors of ATA and AAT. And after we do this, then we are able to get the values of U and V. So let's get started with 26, 18, 1874. So we're solving for the eigenvectors. So we want to set this quantity, 74 minus lambda equal to 0. Okay, and we get our characteristic polynomial here, 74 minus lambda minus 18 squared equals 0. And we can solve this to be lambda 1 equals 80 and lambda 2 equals 20. And an interesting property about these two is that our eigenvalues are actually shared across both ATA and AAT. So once we calculate it for one, we don't have to calculate it for the other. Okay, so then we get our okay, so then let's solve for our eigenvectors. So the first thing is 26 minus 80, 18, 18, 74 minus 80, and this turns into negative 54, 18, 18, negative 6. And obviously this corresponds to the eigenvector 1, 3. And for lambda 1, lambda 2, we get 6, 18, 18, 54 using the same subtraction from ATA. And we get the eigenvector of negative 3, 1. Okay, so now we have our eigenvectors. So now we're able to get V. V is just your eigenvectors except normalized. So we can just write V as 1 over root 10. Maybe I should zoom it in so you can see a little better. 1 over root 10 over 3 over root 10, negative 3 over root 10, and 1 over root 10. Okay, so we have solved for V. Okay, so next up we're going to solve for U. So there's two ways we can solve for U. We'll go over both of them. So I'll say the normal way. And there's a shortcut, but sometimes it's not the shortest way, so we'll call it the shortcut. Okay, so the normal way is just solving for the eigenvectors of AAT. Okay, and remember that our eigenvalues are the same. So we can just find the eigenvectors first of negative 30, 30, and negative 50, 50. And obviously this goes to 1, 1. Okay, and then for the next one is 20, which corresponds to 30, 30, and 10, 50, 30, 30. Which corresponds to 1, negative 1, or the other way around, it doesn't really matter. Okay, so then we get this matrix, 1, 1, 1, negative 1. And make sure that your eigenvalues are lined up. So in our example, we have lambda 1, the eigenvector by lambda 1 as this column. And so obviously we need the eigenvector of lambda 1 as this column. Make sure to keep track of this in your calculations, otherwise you'll get a wrong SVD. Okay, so now we have this, and then we just normalize it. So this just turns into 1 over root 2, 1 over root 2, 1 over root 2, negative 1 over root 2. Okay, so this is our matrix U. Okay, so let's just box that. Okay, so now that we have our matrix U, then we can just go to our sigma, and then we'll be done with our SVD. Okay, we'll go over the shortcut after we're done so we can compare the two. So our sigma, as always, is just the square root of our eigenvalues. So root 80 and root 20. Make sure these line up once again. So this is just 4 root 5 and 2 root 5. Okay, so now this is done. And we are done with our SVD. We have sigma, v, and u. And we can just write it down, I guess. So 1 over root 2, 1 over root 2, 1 over root 2, negative 1 over root 2. Then we can get v, or sigma, 4 root 5, 2 root 5, 0, 0. V transpose turns into 1 over root 10, negative 3 over root 10, and 3 over root 10, and 1 over root 10. Okay, so let's verify this. Oh, whoops, I had a sign change here. Okay, so this should be negative, and this should be negative. Okay, and that's just to keep consistent with this because we had our negative 3 first. Okay, so yeah, so if we expand this, we should get the right answer. Let me pull up the calculation. Okay, so here is our right answer. All right, now we can do the other method, which is the shortcut. Okay, so the shortcut is just we can use a step in between that says AV of I. Oops, is my pen not working? Okay, so we can do AV of I is equal to sigma of I, U of I. So we can just change this to the form 1 over sigma I, A V of I is equal to U of I. Okay, so we can just do this for the only two that we have. Okay, and this is to get the values of U, which normally we would calculate by AAT. So the first one is 1 over 4 root 5, our original matrix, 5, 5, negative 1, 7, times V of I. V of I is this, so 1 over root 10, 3 over root 10, negative 3 over root 10, and 1 over root 10. Okay, and so then we'll get, oh wait, whoops, we should be doing these calculations separately. Okay, pretend I didn't write that. Okay, so we should do these calculations separately. The first one yields 1 over root 2, 1 over root 2, and the second one, if we multiply this here, we would get negative 1 over root 2, 1 over root 2. Okay, and this yields u equals 1 over root 2, negative 1 over root 2, 1 over root 2, 1 over root 2. Okay, and then this ends up producing another valid SVD of the matrix. So if we can verify this through expansion once again. So I'll pull up that. Okay, and we get 5, 5, negative 1, 7. And notice that the U corresponds correctly with our respective SVD values. So here are two ways to find the SVD, and I hope this is useful, especially for those in linear algebra. And yeah.